Welcome back to the course of crystallography. In the previous class, we were discussing about the unitary structure factor and the E values. So, we will see how these E values, the normalized structure factors, can be utilized to determine the centrosymmetric or non-centrosymmetric behavior of a crystal. So, the distribution of E HKL is independent of cell dimensions and the contents of the unit cell. Rather, it is dependent on the presence or absence of the inversion center. So, here in this table, we have a set of theoretical values for the values of E, and what we see here, the average value of E square is same for both centrosymmetric and non-centrosymmetric structures. But when we try to calculate the E square minus 1, the mod of E square minus 1, the centrosymmetric structure should have the value very close to 1, that is 0.968. For non-centrosymmetric structures, it should have value close to 0.73. So, from a real data, when these E square values are calculated and then the mod of E square minus 1 is determined, the value indicates whether it is a centrosymmetric or non-centrosymmetric structure, and then there are indications of how these E values fall rapidly in number of percentages, in terms of percentages when mod E is greater than 1, greater than 2 and greater than 3 and so on, which means the stronger values, stronger reflections are less in number, where these reflections are strong reflections and these are the weak reflections. So, these are different mathematical understanding to talk about the phases, but these phases are very difficult to determine, and then from there it is difficult to arrive at the atomic coordinates using the Bragg-Leibson plot. So, what we need for a practice, routine practice, the phase determination in practice that we do using computer program, we need to guess the phases of sufficient number of reflections with high E values to carry out a meaningful Fourier transformation of HKL, FHKL, to get the reasonable values for rho xyz, which indicates the atom positions. So, to do that, we need the number of phases to be guessed, that depends on the number of atoms in the molecule. Generally, we need about 10 reflections, the phase of 10 reflections to be guessed per atom to get a reasonable structure of a multi-atom structure. So, for this we use a method called symbolic addition. So, based on this method by Zakarian, which was introduced in 1952, a new method was implemented for structure solution. This method starts with guessing the phases of a few reflections with very large values of E. Based on these phases, other phases are ascertained and the Fourier transformation is done to get the electron density. So, this is a random process, this is a guess and assumption. So, what we try to do is that we arrange these reflections in terms of decreasing values of E. We utilize a computer program to guess the phases of such reflections randomly, and then we carry out repeated Fourier transformations and generate a set of electron density of various locations, and then plot those electron densities and try to see whether those electron densities have appropriate bond connectivities or not. So, to do that, initially this method was first used for centrosymmetric structures, and then this was extended for non-centrosymmetric structures as well. So let us concentrate on a simple system where it is either a triclinic, monoclinic, or an orthorhombic lattice. So what one can consider in these three different types of lattices is that if we draw an orthorhombic lattice, which I am trying to draw here, we know that there are several inversion centers possible in case of a centrosymmetric orthorhombic lattice. So we need to identify those points with a certain number. The points which are the corner points are to be numbered as 1. The edge centers on one side, these are numbered as 2. The edge centers on the third side, second side is numbered as set of 3, and the edge center point along Z is numbered as 4. Other than these, there are other symmetry equivalent positions and there are other inversion centers, which is the face center here marked as 5, the face center here marked as 6, face center there marked as 7, and the body center point marked here as 8. So there are 8 inversion centers possible in this orthorhombic unit cell. So for this structure, one can write FHKL as equal to 2 times sum over j equal to 1 to n Fj cos 2 pi Hxj plus Kyj plus Lzj. Suppose we first consider the origin to be located at 1, and then we assume that we are shifting the origin to 2. So if we do such kind of origin shift, so what should happen is the value of x, which was with respect to origin 1, should become x minus half with respect to the origin 2. So in that case, the modified FHKL, that is FHKL dash or FHKL prime, should be equal to 2 times, this should be n by 2, j equal to 1 to n by 2 Fj cos 2 pi Hx minus h by 2 plus Ky plus Lz, or that can be written as 2 times sum over j equal to 1 to n by 2 Fj cos 2 pi Hx plus Ky plus Lz minus pi h. So this can then be rewritten as 2 times sum over j equal to 1 to n by 2 Fj cos 2 pi Hx plus Ky plus Lz into cos minus pi h plus sin 2 pi hx plus ky plus lz into sin minus pi h. You may be thinking how we have written that. So, we assume this as cos a minus b. So, cos a minus b can be written as cos a cos b plus sin a sin b. So, here it is a and that is b. Cos a plus b equal to cos a cos b plus sin a sin b. So, now as cos pi h is equal to minus 1 to the power h and sin pi h is equal to 0 for all h equal to integer, we can simply write f HKL prime as equal to 2 sum over j equal to 1 to n rather n by 2 fj cos 2 pi hx plus ky plus lz into minus 1 to the power h, or we can write f prime HKL equal to minus 1 to the power h into f HKL. So, this particular shift of origin from 1 to 2 will change the sign of f HKL if h is odd. So, the sign of f HKL will be changed if h is odd. That is the sign of the phase of f HKL. So, similarly, if we shift the origin from 1 to 5, that means we change it from here to there. So, what will happen is we will arrive at an expression f HKL prime is equal to minus 1 to the power h plus k f HKL. So, in that case, the sign of phase will change if one of h or k is odd, but not when both are odd or both even. So, these signs or symbols of these phases will help us in guiding to guess the correct phases of various reflections. Here we have a particular tabular form where we have listed what should be the signs of phases of various sets of reflections with the values HKL even, odd even, like here. So in this case, there are different possibilities of the HKL reflections, having the indices as all even or all odd, or combinations of odd and even. So this indicates that all the HKL reflections, when it is all even, which is the first column, all of them have the same phase, and they do not change the phase if the origin is shifted from 1 to 2 or 1 to 3. So any shift of origin from 1 to 2 or 1 to 3 or 2 to 3 or 1 to 5 or whatever does not change the sign of these phases. So it means that the reflections with all even integers, that is all even h, k and l, are structured semi-invariants and their phases cannot be changed in any condition. So what we then try to see that all other reflections have either positive, so you have this case where you have plus sign for 4 of them and the corresponding minus sign for 4 of them, and this is valid for all other reflections where you have 4 plus and 4 minus possibilities. So when we have such situation, then depending on the data set, what we first do is we arrange them with the EHKL mod EHKL values in the decreasing order, and then identify some reflections H1, K1, L1, H2, K2, L2 from top to bottom, and then arbitrarily first assign their phases to be either positive or negative. So for example, suppose if we take a reflection 742 which falls in the class of odd even even. So when we have this reflection odd even even, the 4 possibilities where the phases are plus are marked here. So at the origin 1, 3, 4 and 7 they will have plus phases. So by assuming this to be correct, we try to assign the phase of some other reflection which may be falling like 516, a strong reflection, and that 516 falls as odd even set of reflection. So the odd even comes here. So now with plus sign of 742, the odd even has plus signs for 2 cases, the origin at 1 and origin at 4. That means the choice of origin for 742 was 1, 3, 4 and 7, but now for 516 reflection that choice is now reduced to 1 and 4. So now if we then choose one reflection which is suppose like 1 to 1, which is also probably a strong reflection, which is odd even odd set of reflection, so odd even odd should have all 3 plus, the option is only 1. So now with this condition, the phases of these reflections are all plus, you have choices of those origins. So like that, we try to assign phases of a large number of reflections. How many? As we indicated, 10 reflections per atom. So if it is a 30 atom structure, then we need to guess about 300 such phases. And then after guessing those 300 phases, we use those 300 FHKLs to generate the corresponding rho x, y, z using the Fourier transformation method. And then by doing a Fourier transform, we try to, what we get is some location of electron density in space. Then by applying our chemical knowledge, we try to join those electron densities by bonds and try to see whether that generates something sensible. And then we take that as a starting model and continue the process of guessing phases to completely solve the structure. So once we have correctly guessed a molecule, part of a molecule, maybe like a benzene ring or whatever, so then these are used as known locations of the atoms. So now the rho x, y, z is known. What we do is then do the inverse Fourier transformation and try to get the residual density from a delta F synthesis, and we try to complete the structure. And if this phase guessing method is wrong, that means we start going back and forth in this method. So if the phase of 516 had to be minus, then the choices are different. So if we want to have a 516 to be minus, so with plus sign of 742 here, 516 minus is possibility here, which is 3, and the possibility is 7. That the choice of origin. So now for 1 to 1 to have a plus sign matching with plus and minus of the first two, so we should have plus minus, can have plus here, plus minus is having minus there. So the only choice is now reduced to the origin 3. So this method of guessing, doing Fourier transformation, getting the atom coordinates, trying to see whether it forms a molecule or not, going back and reassigning the phases, changing the phases from plus to minus for centrosymmetric structure is done by a computer program. And nowadays, as we have seen, we know ShellX does this job very well, and we use ShellX S for structure solution, which we will show in one of the lectures how ShellX does this routine structure solution algorithm to get the correct phases, and from there it does a Fourier transformation to give you the correct positions of the atoms. So this method was extremely difficult until and unless the computer programs were incorporated, and these phases had to be done by hand, and it used to take a large amount of time to solve one structure. Not too many years ago, about 30 years ago, this was reasonably difficult, but after ShellX came into picture in 1970s, this random phase determination and simultaneous Fourier transformation has become significantly useful for all kinds of centrosymmetric and non-centrosymmetric structures. So with this we will conclude the part of direct methods, and as I indicated, there are other methods of structure determination like Patterson method, So in the next lecture we will try to talk about this Patterson method.